In this video, we are going to cover abstract data definitions and abstract function signatures. So here we have a list of string data definition, and it's one of either empty or const string list of string. And here we have one for a list of numbers. List of numbers is one of either empty or const number list of number. And you can imagine copying and pasting this to make one for list of booleans, list of images, list of persons, etc. But since there are a lot of similar pieces, right, the only differences are this string and this number and the name of the data type. Instead, we can have data definitions over some x, like functions. So we're going to see this notation a lot more. So list of x is one of either empty or const x list of x. And someone has to pass in this x like a function. All right, so you're going to see that shorthand a lot more. Like here, for example, list of number, and this number replaces all these x's, like so. And that is abstract data definitions. Now let's move on to abstract function signatures. So here is the abstraction keep if from the previous videos, which we derived from seeing two functions that were similar in structure, and we abstracted the differences into parameters, like so. And we have two functions that use keep if, right? Positives only, which takes a list and outputs only the positive numbers. So -4, -1, and 0 are not positive, and we only have the output list 9. And no yelling as well, which consumes a list of string and produces only the strings that have lowercase letters. So this O is capitalized in no, and therefore it's not in the resulting list here, right? So sometimes it's going to be the case that you start off with a function definition and you have to work backwards to the purpose statement and the signature. And this is especially the case when it comes to abstraction, that the signature is the hardest. So let's walk through how you deduce the signature for keep if. One way to deduce the signature for keep if is to look at what the function does with its arguments. For example, lst here. I know the name kind of gives it away, but pretend it's not so obvious, all right? So it looks like it gets consumed with empty and first of lst. And if you look in the documentation, it requires that its argument has to be a non-empty list, right? So we see that this lst is going to be a list of something, and they give it to us right here. All right, what about this fn here? Well, if we look at all the uses of fn, right, this one over here, it comes right after an opening parentheses. So this has to be an operation, right? It has to be a function that consumes and produces something. So let's write that down like so. All right, what does it produce? Well, if we walk backwards, let's see, it looks like it gets fed into this if, the first argument of if, and that has to be Boolean if we look in the documentation. So there we go. We don't know what it consumes yet because we haven't really seen what this is a list of yet. It doesn't really tell us the types yet, so that's fine. We'll just ignore that for now. What does this function produce though? Well, it looks like we use const, and const produces a list. And it looks like if we keep doing recursion of keep if, we'll hit this base case, which is also going to be a list. So it has to produce a list. So list of ... and we don't know the types yet, right? So how do we reduce the other types, right? These over here. Well, we have to look for uses of this function, right? So positives only uses keep if, and it passes a function. So a function that consumes a number produces a Boolean, right? That's the signature for positives, and then an lst here, which is over here, right? All right, what about no yelling? Because it also uses keep if. Well, looks like it uses string lowercase, which I know the signature is a string to Boolean function. And this lst for no yelling is going to be this list of string, right? So let's actually plug one of these into this signature, right? So let's see, let's do this one, list of number, lst. So if we pass in list of number into the keep if function signature, then this lst, right, is the second argument, is going to be list of number, right? So like so. And since this is a list of number and we're taking the first of the lst here, right, then this also has to be a number, right? Because fn is going to consume a number, because first of this lst, we saw that lst is list of number. So it has to be a number. All right, so it produces, it looks like we just take the first of lst here when we're making this list, right? So it has to be a list of number. All right, we don't really do anything to the first of lst, so that's why it's just, a number. So we're building a list of numbers, like so. So let's just uncomment this out and hit run. and we see that we get a lot of signature mismatches, right? Why is that? Well, if you look at these errors, they're saying strings. They're passing strings into the signature that is list of numbers, number, number. So we can write string here, but then it won't work for positives only, and etc. So what we need here is a new notation. We need these arguments here to be more abstract, right? You want this, because we know that keepif works for no yelling and positives only, because it doesn't throw any warnings here, all the tests pass. So what we're going to do is we're going to notate it by replacing these concrete types by %x. That's how you write a variable, right? A type variable. And someone has to plug in this for the concrete types here. So in this case, for no yelling, it's going to be all these x's are going to be replaced with strings. And then in the case for positives only, it's going to be replaced with numbers, all right? And that's how we'll notate abstracting function signatures like so. That is also why I recommend leaving function signatures to sometimes be comments, because if you're not sure, you should just make it a comment like so. But if you can make it a check signature, then you'll reap the benefits of better error messages. Anyways, the book defines it like this, right? This is the notation they use for signatures. So it means it's pretty much the similar thing, right? This square brackets over x says someone's going to plug in this x, right? It's like it kind of represents this parameter list, and these x's are going to be replaced with some concrete type like so, right? So you're going to see this notation, and it's either one is fine. I prefer the check signature version. I prefer getting my checked signatures right so I can use them as holding still and giving me better error messages. Anyways, let's move on to due to all. So here we have our due to all abstraction, and we're going to walk backwards and deduce the signature from there, all right? So let's look at this function and what it does. It consumes two arguments, so those dots there, and produces something, right? So the first argument, fn, it looks like it consumes the first of the list, right? So first of LST, I know the name makes it obvious, but pretend it's not so obvious, right? The second argument is going to be list of something. All right, the first argument, it's then passed into the first argument of fn, which is the first argument of due to all. So this first argument of due to all is going to consume something and produce something. All right, and then this whole function, right, it has a cons and an empty, right? Empty for the base case and cons over here for the else case. So we see that it has to produce a list of something. All right, so how do we plug in these concrete types? Well, we have to look for uses of due to all and then work backwards from there, right? So here's square all. It consumes a list of numbers and scores all the numbers in the list. Wait, 1 squared is 1, 2 squared is 4, 3 squared is 9. And here's one for wordlen. It consumes a list of words and it turns them into numbers. That is the count of the letters. Samu is 3 long, wolf is 1, 2, 3, 4, and meow is also 4. All right, so let's write these signatures here for this due to all. It consumes a square function. So this function consumes a number, produces a number. All right, and this LST is going to be of type list of number. Let's do the same thing for word length here. So string length is going to be a function that consumes a string and produces a number. All right, and then LST here is a list of string for word length. All right, so let's plug in this one first. All right, square all. So this list of number, right, is going to go to the second argument of due to all. So this is going to be list of number. If this is a list of number, then this function consumes the first of LST, right? And we saw that LST is a list of number. So it's going to consume a number here. All right. And then what does it produce? Well, it doesn't say anything, but if we look at the signature here that uses due to all, right, we said that it's a number to number function. So let's just fill that in. And since this function produces a number, right, this function produces a number, we're just using cons on this, right? So this type is going to be the output type of the list here, right? Whatever this function produces, right, is going to be the answer for what this whole function produces as a list, right? So like so, right? So if we run this, it does work for square all, but it's not going to work for wordling, right? Why? Because it's turning strings into numbers. And we see the errors here, right? We're seeing signature violation, right? Someone's passing in a list of strings instead of a list of numbers here. So, right, that's fine. Maybe we can just replace all these with %x, right? Like so, right? So %x. So if this is %x, right, then the function that this first argument here is going to consume the first of the list of %x. So this has to be %x, right? What does this have to reduce? Well, it looks like %x again, because this is also a number. And then since this is a %x, right, it's going to get fed into this cons here. So this output type has to be there. Let's just run this, and it looks like all 7 tests passed. But this is wrong. And if you were to program in other programming languages, it would not work for a wordling here, right? Because let's plug in the concrete types here for string, right? So if I do, I'm going to copy and paste this actually. And let's replace x with string, right? We're going to see why it doesn't work. %x with string, right? Like so, right? Why is this not valid for this wordlen function over here? Well, because this function, string length, is not string arrow string, it's string arrow number, right? So that's wrong. And also, it doesn't produce a list of string. This function produces a list of number, right? So again, in other programming languages, there will be more strong, there'll be more enforcing of this where you have to get your types right. So what we really need is another type variable. Why? Because I just plugged in, right? I just replaced all these %x's with string and compared it with a function that uses due to all, and it doesn't work out. The math isn't mathing. So we need another type variable. So, all right, we'll keep %x, right? So this, what we're trying to encode is this, right? Because this is the signature for wordlen all in terms of due to all, right? So let's actually fill in the new types here, right? So it consumes a list of string. That's fine. We'll leave it as %x, right? So that's fine. But what about this? So this is also fine, %x, right? It's going to be string, but this number, right? This number, this can't be an x. This has to be a y, %y. Why? Because this is a number, it's independent from these %x's, because we assign %x to be strings, right? So this %y, right? This function is going to be something that consumes a string and produces a %y, where this could also be a string, but in this case, for wordling, it's a number. All right, and this %y, right, since this function produces a %y, right, it gets fed into this cons, and this cons builds a list of %y. So this is the final signature for due to all that is most accurate, right? So we run it, it's also fine. But again, in other programming languages, if you just write %x everywhere, it's not going to work out. All right, so let me copy and paste in the finishing signature from the book, right? It's the same notation, different notation, right? We're going to receive an x and y, and you're going to have to plug in these types here, like so. All right, but that is how you type the signature, abstract the signature for due to all. Now let's move on to the next function. The next abstract function that we're going to have to write the signature for is collapse. So I recommend you pause the video and try to write the signature for collapse. All right, it's going to be a little involved, but see if you can follow the process that I did for the other previous functions. All right, spoilers in 3, 2, and 1. All right, I'm assuming that you guys took a good swing at it, so now let's go over it together. So walking backwards, right, LSD here is the third argument to collapse, and it gives us a hint as to what it is. Right, it's consumed by first and empty hall, so this has to be a list. So list of, let's say, %x, %x, so I can type that finally. All right, what about the second argument to collapse? It's called base. So this can be %x, but it can also be %y, right? Because there's nothing restricting it to be something other than %x. And you'll see, I'll explain why in a moment. So this is going to be %y. It can be a type different from the list that we're passing it in. So %y. All right, what about the first argument to collapse? Well, it's going to be a function because it's coming after this opening parentheses. So it's going to be a function that consumes two arguments. This is the first argument, this is the second argument to this function. So we need a parentheses, dot, 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 first argument, second argument is going to produce something because it's a function, all right? What does it consume and produce? Well, it consumes as its first argument, as first of LST. Well, we said LST is a list of %x. So taking the first of this list, %x, is just going to be the type %x, like so, all right? What about the second argument to this function, right? So we established the first argument is %x. The second argument is going to be eventually, right, this function keeps calling itself recursively until it hits the base case. And we see the base case is %y. So the second argument is %y, right? The type y, all right? And then it's going to produce some type y because eventually this function is going to hit the base case. It has to be something that combines the base case, right? And something that combines with the base case has to be producing the base case, all right? And then this whole thing produces the base case, right? Because eventually this hits the base case and yeah, this has to combine with the base case. So this is the type signature for collapse. Why is it the type signature for collapse? Well, if you deduce it from these two functions, you won't get the correct answer because this function, sumNums, that uses collapse, just takes in a list of numbers, add, which consumes numbers, and 0 is also a number. And same for fuse strings. It's a string, right? String appendix and strings. The base case is also a string, and then it consumes a list of string, right? So what you need to do in this case is that you need to come up with a new example that really stretches out the use of collapse. For example, word count over here, right? So word count consumes a list of strings and produces a number, and it just counts up how many letters are in the list here, right? So it uses collapse. What is the signature for word count? Well, it passes collapse these arguments add word len. And add word len is a function that consumes a string and a number and then produces a number. So string to number, right? String number, two arguments I've had, and produces a number. The base case here is a number, right? It's 0. And then it consumes a list of string, right? So list of string. And from this signature, you'll be able to deduce these x's and y's. From these signatures, if you just use one type, like 0, which is a number, a list of numbers, LST is a list of numbers here, and plus is also a list, and plus also takes in numbers, I mean. Well, you're not going to come up with the right signature. You're going to come up with %x, 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 %x. You have to really stretch your mind out and write down a function that's complex and consumes types, right? Transforms, consumes different types, like so, right? This one, list of string, right, is different from this number as the base case, which is different from this add len, which is consuming a string and a number and produces a number, right? And again, from this, you can derive this. If you plug in the types here, like so, right, then you'll get the correct answer, right? So everywhere you see %x, replace it with string. Everywhere you see %y, right, replace it with number, and you'll see why it works out. Again, these are two type variables, x and y, and this y could be the same as x, but it can also be different. So yeah. Anyway, let's just run this, and we see that it passes all these tests. And that is how you abstract function signatures. You have to walk backwards. You have to sometimes look at the uses of the abstraction and come up with more complex examples that use that abstraction, that consume and, spit out different types. All right. Anywho, that is about it for this video, and I will catch you in the next one.